Graph neural networks, GNNs, have achieved remarkable success in graph analytical tasks, but their effectiveness is often compromised by distribution shifts in real-world scenarios. Unsupervised Graph Domain Adaptation, UGDA, aims to facilitate knowledge transfer from a labeled source graph to an unlabeled target graph. Existing UGDA efforts primarily focus on model-centric methods, which have inherent limitations. A data-centric approach that modifies the source graph has demonstrated considerable potential. This work investigates the limitations of existing model-centric UGDA methods and proposes a data-centric approach guided by two principles: alignment principle and rescaling principle. The alignment principle suggests reducing the discrepancy between the modified source graph and the target graph, while the rescaling principle states that a smaller graph modified from the source graph can achieve a generalization error comparable to that of a larger graph. The authors propose a novel UGDA method, GraphAlign, which generates a small yet transferable graph for GNN training. GraphAlign employs a surrogate GNN model to map graphs into Euclidean representation spaces and utilizes a maximum mean discrepancy, MMD, distance as the discrepancy metric. The generated graph is expected to have a much smaller size and retain sufficient information from the source graph. The contextual stochastic block model, CSBM, is used to generate random graphs, facilitating the examination of domain shift. A motivating example demonstrates the inherent limitation of current model-centric UGDA methods, and propositions highlight the potential benefits of adopting a data-centric approach in UGDA. The generalization bound for UGDA is derived, laying the theoretical foundation for the alignment and rescaling principles. The proposed method, GraphAlign, generates a new graph to replace the source graph for training, adhering to the alignment and rescaling principles, and aiming to create a new graph that is much smaller, aligns well with the target graph, and retains enough information from the source graph. The optimization problem is formulated to guide the alignment of the generated graph with the target graph while incorporating sufficient information from the source graph. Here is a combined summary of the 4 pages. GraphAlign, a novel approach to graph domain adaptation, is introduced to address the critical problem in graph neural networks. This method modifies the source graph to align with the target graph, ensuring the generated graph retains sufficient information from the source graph and exhibits properties of real-world networks. The approach employs a surrogate GNN model to represent the mapping process, and the generated graph is optimized by minimizing 3 objective functions: alignment, mimicry, and property preservation. The alignment objective, measured using the maximum mean discrepancy distance, aims to align the generated graph with the target graph. The mimicry objective, measured using cosine similarity, ensures the generated graph preserves essential information from the source graph. The property preservation objective, measured using feature smoothness and sparsity, ensures the generated graph exhibits properties of real-world networks. Extensive experiments on 6 transfer scenarios demonstrate that GraphAlign outperforms various baselines, including vanilla ERM, non-graph domain adaptation methods, and UGDA methods, with an average improvement of plus 2.16% over the best baseline. Ablation studies validate the effectiveness of each component in GraphAlign, including the initialization strategy, the alignment principle, the gradient matching strategy, and the preservation of graph properties. The analysis of hyperparameters shows that GraphAlign consistently outperforms the best baseline model across different settings. Furthermore, GraphAlign performs well under various levels of domain shifts, and its versatility is demonstrated by combining it with different GNNs and model-centric UGDA methods. The runtime comparison shows that GraphAlign is comparable to vanilla ERM methods, yet delivers superior performance, making it a novel and effective approach to address graph domain adaptation. Here is a combined summary of pages 912. This research introduces GraphAlign, a novel approach to unsupervised graph domain adaptation, UGDA, that focuses on modifying the source graph data to enhance transferability across different domains. GraphAlign aligns the source and target graphs by minimizing the discrepancy between their distributions and reducing the scale of the source graph, thereby making it more adaptable. This is achieved through 2 key principles: alignment and rescaling. The authors provide a theoretical analysis of the generalization bound for UGDA, demonstrating that a smaller-scale source graph can be more effective in enhancing transferability. They propose a data-centric approach for UGDA, which differs from traditional model-centric methods that focus on learning domain invariant representations or utilizing adversarial training techniques. The paper reviews existing UGDA methods, including those that minimize domain discrepancy metrics and those utilizing adversarial training. It discusses the concept of data-centric AI, which emphasizes the importance of data modification over model design, and references various studies on graph neural networks, domain adaptation, and graph condensation or sparsification. The GraphAlign framework is presented, including the initialization process, which creates a generated graph with plain nodes, computes the adjacency matrix, and assigns labels to ensure the same distribution as the source graph. The algorithm utilizes techniques such as Wasserstein distance, Laplacian, and diagonal degree matrix to achieve optimal graph alignment. The authors highlight the importance of addressing graph domain adaptation and the potential benefits of modifying data to achieve this goal, demonstrating the novelty of their approach. GraphAlign is a novel algorithm proposed to address the problem of graph domain adaptation by modifying the source graph to align with the target graph. The algorithm consists of two main components: initialization of the modified graph and training of the graph neural network (GNN) model. The initialization step is crucial, and the authors compare their proposed method with several baselines, demonstrating its superior performance in most cases. They also investigate the impact of initialization on the loss convergence of the GNN model, showing that the proposed initialization significantly enhances the optimization process, resulting in improved convergence characterized by a reduced loss. The authors evaluate the transferability of GraphAlign across graphs with different homophily, comparing its performance with several baselines. The results show that GraphAlign outperforms the baselines in most cases, demonstrating its effectiveness in addressing graph domain adaptation. Additional experimental results include the performance of GraphAlign under different initialization methods and the impact of GraphAlign on the eta parameter, which affects the generalization bound for UGDA. The results show that GraphAlign effectively reduces the value of eta, highlighting its superiority in modifying data to address UGDA. The paper also explores the concept of graph domain adaptation, discussing the limitations of existing efforts and proposing the new approach of GraphAlign. It provides an analysis of the performance of the model under different levels of homophily, demonstrating that as the homophily ratio decreases, the performance of the model increases, indicating its effectiveness in handling more complex domain shifts. A visualization of node embeddings inferred by UDA GCN and GraphAlign models is presented, showing that GraphAlign produces more concentrated clusters of nodes in the same class. The paper concludes with theoretical connections between the property of the newly generated graph and its implications for UGDA. It provides a detailed proof for two propositions, utilizing concepts such as the Frobenius norm and Hoeffding's inequality to support its claims. The proposed GraphAlign algorithm demonstrates its effectiveness in addressing graph domain adaptation by modifying the source graph to align with the target graph, outperforming several baselines and providing a promising solution for real-world applications. Graph domain adaptation is a critical challenge in machine learning, where the goal is to transfer knowledge from a source domain to a target domain with a different distribution. This research paper explores the concept of graph domain adaptation, focusing on the transferability of graph neural networks, GNNs, between different graph distributions. The authors propose a data-centric approach, demonstrating that modifying the data can lead to improved adaptation performance. The paper begins by analyzing the optimal classifier in the source domain, deriving an upper bound for the classification error in the target domain. Theorem 1 provides a bound on the target error in terms of the source error, alignment term, and rescaling term. This theorem is crucial in understanding the relationship between the source and target domains. The proof involves introducing an inequality that links the target error to the optimal combined error, alignment term, and rescaling term, and further deriving the inequality using the Cauchy-Schwarz inequality. The paper also introduces Theorem 2, which focuses on the transferability of GNNs. This theorem states that the difference in representations between two graphs is bounded by the spectral distance between the graphs. The proof involves analyzing the GNN model, specifically a Clayer GCN with a one-hop polynomial filter, and deriving an upper bound for the hidden representation difference between two graphs. Furthermore, the paper investigates the theoretical connections between Wasserstein distance and maximum mean discrepancy, MMD, distance in the context of graph domain adaptation. Theorem 3 establishes a connection between the two distances, demonstrating that MMD distance can provide a bounded interval for the Wasserstein distance. The proof involves defining the MMD distance and Wasserstein distance and deriving a link between them using properties of reproducing kernel Hilbert spaces, RKHS. This connection has significant implications for developing algorithms that can efficiently estimate the Wasserstein distance using the MMD distance.